Head and neck squamous cell carcinomas are the sixth most common cancers worldwide. Head and neck cancers are classified as HPV positive if it is caused by human papillomavirus and HPV negative if it is caused by alcohol, smoking, or other carcinogens. Gene expression is modular in nature. And although single gene differential expression analysis aids our understanding of disease mechanisms, it lacks the context incorporated by gene co-expression networks. In this project, we compare three module detection methods and demonstrate how module detection, in addition to the single gene differential expression analysis, could support novel biomarker discovery. For this project, we used the TCGA's head and neck cancer dataset. This dataset contains 548 samples and 60,000 genes. We focused on the two phenotypes, age and HPV status, and performed the analysis separately. We first filtered the data to exclude samples without the phenotypic information. We then removed the genes with low variation using the counts per million filter and the median absolute deviation filter. This filtered dataset is used for single gene differential expression analysis using three different methods, lemma, LM, and DC2, followed by the pathway enrichment analysis on the differentially expressed genes using the HiPAR tool. For module detection, we further filtered this dataset to only include genes from cancer, immune, and metabolic pathways to reduce the computational complexity. Module detection was performed using three different tools, Magena, WDCNA, and ICA. We subsequently performed differential connectivity analysis on the modules detected by each method using the Conan tool. We selected differentially connected modules and performed the pathway enrichment analysis using HiPAR. Finally, we compared the pathways identified as enriched across methods and modules detected by each method.
Moving on, we used HiPAR to look at the differentially connected modules in all of the different module detection methods. And here we see that in Magena, ICA, and WGCNA, there are various different modules with different enrichment of different gene pathways. Specifically, of the most interest here, all three module detection methods show enrichment for the P450 pathway, ABC transporters pathway, and the retinol pathway, all upregulated in the HPV negative samples, meaning there is a higher connectivity in the HPV negative samples. And this is reflected through past literature. Of note here, these are not identified as significant pathways through single gene differential expression methods. Moving on to look more specifically at the overlap between pathways enriched across module detection methods, we see that there are 87 pathways enriched in only one of the module detection methods, 53 enriched in exactly two of the module detection methods, and 7 pathways enriched in all three module detection methods. And all of these pathways identified as enriched in all three of the module detection methods have previous literature which support them in the head and neck cancer field. With, again, ABC transporters, retinol metabolism, and P450 related pathways being novel within this context, as they don't show up in single gene differential expression gene pathway enrichment and are supported by past literature.
I'd like to highlight some pathway enrichment results. The H phenotype in head and neck cancer shows weak transcriptomic signal and no module detection method identified differentially connected modules between the old and young groups. In HPV status, however, significantly differentially connected modules were found between the negative and positive phenotypes. The P450 cytochrome pathway, which is associated with the metabolism of xenobiotics, the ABC transporters pathway, and retinol pathway are all known to correlate to HPV negative status, according to previous literature. these pathways are detected by all three module detection methods, significantly connected to HPV negative status. All three single gene differential expression analyses failed to detect this signal. The EMT pathway connected to poor prognosis and mTORC1 in HPV negative cancers, however, were detected by both module detection and single gene differential expression methods. To compare module membership, we looked at a pairwise comparison of significantly differentially connected modules and HPV status for each module detection method. Our overlap measure used was overlap over the size of the smaller module being compared. Overall, there was not a lot of similarity between module detection methods modules. Megina and ICA had very little overlap between their modules. WGCNA and Megina's results showed that in some instances, one WGCNA module encompassed multiple Megina modules. And finally, WGCNA and ICA had a handful of modules overlapping. For a comparison in terms of usage of the tools, WGCNA ranks higher in terms of ease of use, computational efficiency, and sensitivity. ICA requires the user provide the number of modules desired, which is difficult to choose and can significantly affect results. ICA is also computationally expensive. Megina requires extraction of leaf modules from results and needs parallel computing for computational efficiency. Both WGCNA and ICA produce larger modules, while Megina produces smaller modules, which are subsets of the larger modules produced by the other two methods. And for our acknowledgements, we'd like to thank our co-authors and mentors for helping us with the project, as well as our programs at Boston University, Bioinformatics, and the section of Computational Biomedicine. Thank you.